Okay, YouTube, in this video we're going to focus on problems involving maximizing or minimizing quadratic functions, which is a common occurrence. You see these quite often. So basically what you see here is kind of a step-by-step on how you would get through something like this. And number one, this is my favorite step that it even needs to be listed here, but it says read the problem carefully and decide which quantity is to be maximized or minimized. But I suppose that's probably an important part of the problem. What do you want to make as big or as small as possible? And then number two here says use the conditions of the problem to express the quantity as a function in one variable. So we've done application problems before, and we're going to kind of review how we rewrite things in terms of one variable. But once we get that in terms of one variable, you're going to find that we get this quadratic thing, or this second degree polynomial here. And then we're just going to go, since it's a second degree thing, either find its minimum or maximum value. So recall that if you wanted to find the vertex values here on this parabola, which by the way either opens downward or opens upward, it either has a max or it has a min. If it is in standard form, then we say then really what we're looking for here is the vertex. And the vertex, if it's in standard form, always occurs at negative b over 2a, f of negative b over 2a. So that being said, we're basically looking for vertices here and interpreting their results. So we're going to answer the question posed in the problem, but we say graphically that's what we're doing. So for this checkpoint 6, it says among all pairs of numbers whose difference is 8, find a pair whose product is as small as possible. And I'm going to tell you that we can actually do this now. So we say what is the minimum product and what are those numbers? So let's go ahead and take a look at this right here. We say we want to find a pair whose product is as small as possible. Okay. So what we're trying to do is minimize. I'm going to write a little note here. Minimize the product of these two numbers. So what I'm going to do here is I'm going to say that we have a number one. I guess I shouldn't write number $1, number 1 and number 2. And in terms of their relationship between one another, I'm going to say let x be number 1 here. And what I know is the difference between this number and the other number is 8. So I could say that really this number here is x minus 8. But I'm going to list my two numbers, and you notice that I list them in terms of the same variable with respect to that same thing. But basically, this is what I'm trying to make as small as possible, is the product of these two numbers. So I'm going to write, I want to minimize that, but I'm going to write the product, and I'm going to say x times x minus 8. I want this to be as small as possible here. So we've already decided that we want to minimize the product of these two numbers. We say using the conditions of the problem, we express the quantity as a function in one variable. And so what I want you to notice is this. We have just one single variable here, but we could say that this is our y equals our function of x. We could say also f of x equals this right here. So we're going to rewrite this into standard form. All that really means is once we get this here, we're going to simplify this by rewriting it as x squared minus 8x and put it in the standard form. And I do want to point out that our c value is 0 here. But that's going to be something that doesn't bother us very much here. Next, what we want to do is find the vertex values, what that minimum product would be. Okay. So we would say solving this, what we end up with here is negative b over 2a is what we would search for first, negative b over 2a. So when we find this here, we say x equals negative. Now our b value is a negative 8, and our a value is 1. So we have 2 times 1 here. We get 8 over 2 is 4. So this is the number x at which our minimum occurs for our opening upward parabola here. So we know that the x value at the vertex is this. And I'll go back and interpret this here in a minute. But the important part is that we found one of the critical components of the vertex. Now the other component here we're going to need to find by plugging that x value in. So we say f of 4 in this case is going to be, well, we have x squared minus 8x. So we'd say 4 squared minus 8 times 4, which is 16 minus 32, which is negative 16 here. So we would say negative 16. And yeah, it seems that I have my math correct here. We say 4 comma negative 16 would be this right here. So what we want to look at here is this. Essentially that x is the first number. We have the first number here. And we wrote that over there on the left, that our first number is x. But also the y value at our vertex, this is representing this right here. And that right there was the product of these two numbers. So we say the product of these two numbers. So if I'm saying all numbers with a difference of 8, it seems that the minimum value that we could ever get by multiplying them would be negative 16, and this would have to occur when one of the numbers is 4. So if one of our numbers is 4, I suppose I would say number 1, as the, state an answer to the question posed in the problem here. We say number 1 is equal to 4, and number 2 is equal to, now we had x minus 8, which 4 minus 8 would give us negative 4. But those would be our two numbers there, and they certainly check out. They would multiply out to be negative 16. So in this last problem here, let's take a look at a situation where we'd have to deal with a little bit of geometry. So it says we have 120 feet of fencing to enclose a rectangular region. So I'm going to start by kind of representing our rectangular region here. And I'm going to refer to this just because it's the longer side is the length and this is the width here. But we say find the dimensions of the rectangle, or the length and width, that would maximize the enclosed area. So here, keep in mind that our goal is to maximize this situation. And we talk about the enclosed area as what we want to maximize. So we say, what is the maximum area as well? So let's start with this. Knowing what we know about this, we'd say length times width. What we've been given here is 120 feet of fencing. And what I want to point out is that that is a kind of a perimeter value. Perimeter value here. So this 120 feet of fencing, let's write a little formula here, but we say 2 times the length plus 2 times the width is our perimeter value here. Okay. So I'm going to put a box around that. The other thing is this. The thing that we're trying to maximize is the area of this rectangular space. So that area is given as the length times the width here. So what makes this problem kind of trickier for sometimes is this. We need to, looking at our steps here, this was key here, rewrite the, number 2 here, use the conditions of the problem to express the quantity as a function in one variable. So what you're seeing here is that I've got a couple of functions, but they're expressed in terms of length and width. So what we want to do is this. One thing I know is that the perimeter is 120 feet. So I'm going to go ahead and substitute that in for my perimeter here in this first expression. I get 2 times the length plus 2 times the width. But what we're going to do is this. We are going to solve for L or W. And in this case, I'm going to choose to solve for L. So I get this. I say subtracting 2W from both sides here, we would get that 2 times the length would be equal to 120 minus 2 times the width. And then follow this up with dividing by 2. We would end up with this expression here. The length in terms of the width would be 120 divided by 2 minus 2 divided by 2, which is negative 1 times W. So the reason why we've done this here is because what we're going to do is we're going to substitute this value, substitute for the length in the area equation, the equation that we're trying to find a maximum area for. So substituting this in right here for the length, what you'll see happening here is that we get area is now just in terms of, let's see, 60 minus W times just the width, the W right here. We just substituted in for our L. So with this right here, we could say, well, this is our function of area, and we want to maximize this area. So looking back at our steps again, we said step 3 here would be to rewrite our function in the form ax squared plus bx plus c right there, our standard form. And so what we're going to do is exactly that. We're going to say that I would distribute, and I'll get area equals 60w minus w squared, or I'm inclined to say area, and I'm going to write area as a function of the width here, but is negative w squared plus 60w. I'm going to write this in standard form. Don't worry about the a of w here, but basically the area is this. So what we want to do is we want to find what is the width and the length combination that would cause the maximum area, and what is that maximum area. And what we know is because this is a parabola that I recognized here, opens downward, it's going to have a maximum value, and we're finding the vertex again. So our axis of symmetry here would be at x equals negative b over 2 times a. Our b value here is 60, and our a value is negative 1. So I get 60 negatives over 2 negatives, which is 30. So at our vertex value here, we have the x value is 30. We need to go find now what is that maximum value. So we're going to go plug that 30 into our function to go find the vertex that is at 30 comma f of 30. So let's go plug this in. So now we say f of 30 here. We really should be saying a of 30. So I beg your pardon. We have an area function here. But a of 30 is going to be what we get when we go plug this into our area function here. So we get negative 30 squared plus 60 times 30. So a little bit of mental math here. 30 times 30 is 900, but this becomes a negative 900. And then 6 times 3 is 18 with two zeros after it. Basically, we get 900. And so I would say that our rectangular space here would benefit by having a width that is equal to 30. And I'm going to go put this on our picture here. We say 30. So one thing I also know is that once I have the width here, we can go and solve for the length. Recall that the length is 60 minus the width, which in this case gives us 60 minus this 30, which would show that our maximum area actually occurs when we have a square. This would be 30. Also that our maximum area here was 900 square whatever units, but we would say that we got that by taking our length times our width. So we would say, what are the dimensions? We would say the width equal to 30 units. I didn't disclose what units we were using. Length is equal to 30 units. And we would have a max area of 900 units squared. Cheers.